Right at the center of our galaxy, the Milky Way, there's a glow, a weird high-energy light that's had astronomers scratching their heads for years. So yeah, let's dive into this cosmic whodunit.
You know, when we run into a big cosmic puzzle, our first instinct is usually to look for some new exotic particle. But what if the answer isn't a thing at all? What if we need to completely rethink something we just take for granted? I'm talking about empty space itself.
So for over a decade now, the Fermi Large Area Telescope has been staring, just staring at the heart of our galaxy, and it keeps seeing this extra glow, an excess of gamma rays that shouldn't be there. Scientists call it the Galactic Center GeV excess, and honestly, it's been a real headache to explain.
And we're not talking about just any random light here. This glow is super specific. It's happening in a really narrow energy range, between 1 and 10 giga-electron volts. That precision, it's like a cosmic fingerprint. Whatever theory tries to explain this mystery, it has to match that fingerprint perfectly. Okay, so for a long time, there was a prime suspect. And it was a really exciting one: dark matter. The idea was just beautiful. You have all this dark matter packed into the galactic core, right? The particles smash into each other, they annihilate, and poof, they produce the exact kind of gamma ray glow we're seeing. It seemed to fit perfectly. But you know how these things go. The more we looked, the more the simple, elegant answers started to come apart at the seams. The case against the usual suspects, both dark matter and the other big idea, is getting, well, pretty darn strong. So here's the deal. The dark matter idea is in trouble because, well, we've been looking for it for years with these massive, incredibly sensitive experiments, and we found nothing. Zilch. Not a single particle. Then there's the other theory, a whole bunch of undiscovered, super fast-spinning dead stars called millisecond pulsars. But for that to work, you'd need something like 10,000 of them crammed into the galactic core. And a lot of astronomers are saying, no way. That's too much. It's really, really unlikely. Okay, so we've got a signal, we see the glow, but the prime suspect, dark matter, has an alibi, and the backup suspect, the pulsars, just doesn't seem plausible. So if it's not them, where is this signal coming from? Maybe we've been asking the wrong question all along.
And this is where things get really wild. A totally new idea is on the table. What if the glow isn't coming from a thing in space, but from space itself? What if we have to fundamentally change what we mean when we say empty?
It's a new theory called dynamic vacuum field theory, or DVFT for short. And it basically says the vacuum isn't empty. It's not a void. It's a physical field, something real that fills all of space. And just like the surface of a pond, it can be disturbed, it can ripple, and when it does, it can release energy. This is a huge shift in how we think about the universe. It's this idea that maybe, just maybe, the biggest secrets aren't hidden in some new exotic particle we have yet to find, but in the very fabric of nothing itself.
All right, so how does a rippling vacuum create a specific glow of gamma rays? Well, the mechanism is actually surprisingly straightforward.
See, in this model, a gamma ray isn't really a particle like we normally think of it. It's a vibration, a really, really high-frequency vibration in the vacuum field itself. Think about it like this. A gentle ripple on the pond might be like a radio wave. But if you could make that ripple vibrate incredibly fast and with a ton of energy, that's a gamma ray. So here's the chain of events. Step 1. You've got this immense amount of mass, stars, a supermassive black hole, all packed into the galactic center. That mass literally disturbs the vacuum field around it. Step 2. This disturbance creates these super fast phase fluctuations. Those are the ripples we were talking about. Step 3. As these ripples spread out, they pump energy into the vacuum, basically making it unstable. And finally, step 4, the vacuum has to release that extra energy. And how does it do that? By emitting a glow of gamma rays, which is exactly what we see from Earth. And here is where it gets really, really compelling. This new theory doesn't just kind of explain the data, it nails it. The Fermi telescope sees the signal cut off sharply around 5 GeV. Guess what? The DVFT theory naturally predicts a cutoff right at 5 GeV because of the vacuum's properties. The telescope sees a perfectly spherical glow. The theory predicts that exact spherical shape. And here's the kicker. Other telescopes have looked for a signal at even higher TeV energies and found nothing.
DVFT predicts there shouldn't be a signal at those energies. It just fits. All the pieces just click into place.
And you know what really gets scientists excited about a new theory? When it's elegant. When it just works without needing a bunch of extra bells and whistles. And that's the case here. The detailed calculations show that the core idea is solid. You don't need to add a bunch of complex tweaks or special adjustments to make it fit. The simplest version of the theory does the job. And that, in science, is a beautiful thing.
Okay, but a really great theory doesn't just solve one mystery, right? It should have the power to explain other things too. And this is where DVFT starts to look even more promising.
I mean, we're not just talking about a gamma-ray glow anymore. DVFT also suggests that the weird way galaxies rotate, the whole reason we invented dark matter in the first place, might just be an effect of this vacuum distortion. It could even offer an explanation for other huge cosmic puzzles, like the mysterious cold spot in the cosmic microwave background. It might even give us a way to finally get rid of the annoying infinities that pop up in particle physics. This isn't just one solution. It's potentially a whole new framework for understanding the cosmos.
So where do we go from here? This isn't just some sci-fi idea. It's a real, testable scientific theory, and we're right at the very beginning of its story.
Think about where we are right now. Just this year, new analysis of the Fermi data has made the old models look even shakier. The foundational papers for this dynamic vacuum field theory, they were just published. And looking to the future, the theory makes a clear, testable prediction. It says we should find a similar gamma-ray glow at the heart of other big, dense galaxies, like Andromeda, our next-door neighbor. That gives the next generation of telescopes a specific target, a clear way to see if this whole radical idea holds water.
And that leaves us with this one final mind-bending thought. For centuries, we've pictured the vacuum as, well, as nothing, the empty stage where the real action of the universe happens. But what if we've had it backwards the entire time? What if the nothing we thought was empty is actually the most important, most fundamental thing in the entire universe?